Okay, nice straightforward one this week. We're looking at waves. It starts in a rather strange place, you might think, by looking at Hooke's law, which is kind of going back to some of the material stuff. So when you studied Young's modulus before, it just wants to bring that in again. The reason being is obviously Hooke's law is quite closely related. Well, it's about stretching springs, so applying a force to a spring. What we're doing now is looking at waves and oscillations. So it's the relationship then between an oscillating mass on a spring. Obviously, we'll draw on some of the physics that Hooke's law goes into. So that's why that starts there. Okay, so then we get into a little bit of the basics. So period, frequency, just learning the terminology. Make sure that you go through that and you're quite happy. It's not complicated, but you can't skip it. You need to be able to use the right words for things. Okay, periodic motion. So remember, this is not just about pendulums and it's not just about things bouncing up on springs. Quite a lot of stuff has periodic motion or simple harmonic motion. So this just goes through a few of the main ideas and examples. So specifically, the first bit is looking at systems that are related to Hooke's law. So things that are kind of oscillating on springs. And in point 4, it then looks at the pendulum. These have their own specific equations that you do need to be aware of. But some of the ideas that they bring can be applicable to any kind of oscillator. But if you can study a mass on a spring, then to be honest, you can kind of extrapolate that to a lot of other things. If you just think about like a vibrating atom, for instance, the mass of it is the atom, but the spring is the atomic bond, and it will act very, very similarly to a mass hanging on a spring in the lab. So there's an awful lot that you can learn about stuff like internal energy, for instance, down to the vibrations of solids from studying oscillations on a macroscopic scale. Okay, moving on then to energy. Again, there can be further applications of energy depending on whether you're looking at a pendulum. A pendulum obviously does involve changes of gravitational potential energy, whereas a spring looks at the change in like elastic potential, so that the potential energy stored in a spring, for instance. So again, it's worth just getting your head around the idea that this is applying that conservation of energy. The total energy of an oscillator is always constant. And what it does is it moves between kinetic energy and potential energy. Regardless of the type of oscillator you're talking about, it's always going to be moving fastest at the equilibrium point, which is in the centre. And it's always going to slow down and stop, and therefore have the least kinetic energy, and therefore the maximum potential energy at the extremes, i.e. at its amplitude, when the displacement is equal to the amplitude, i.e. the maximum displacement. So you've really got to be able to understand all the real fundamentals. If any of the words I've just used didn't make sense, you're not ready to study the later sections yet. You've got to get an idea for how things move and what we call those things like displacement, amplitude, equilibrium point, stuff like that. Okay. There are obviously links between circular motion and simple harmonic motion, not just in terms of terminology, but some of the maths actually translates across as well. So 16.6 just goes a little bit into looking at that. For example, relationship between frequency and time period, for instance, or angular frequency is an idea that's used in both. So the last few sections, damped harmonic motion, forced oscillations, really just start to look at, let's say, taking it slightly more real world. So up to that point, you've looked at very theoretical oscillators which just move quite freely. But in the real world, we look at things like damping, and we also look at stuff that is forced to oscillate. That has a lot of applications throughout physics. It's only a small chapter just to look at for now, but those two sections underpin an awful lot of physics. In the wider world, if you, for example, wanted to go into acoustics, then looking at damping and forced oscillations and resonance are vital. The idea of resonance is very understated, but to be honest, resonance is one of the most important ideas that comes up in all sorts of areas in physics. Okay, so 16.9 obviously goes into waves a little bit more specifically. And then we get into the last section, which is second to last section, which is a really important one to study for now, superposition and interference. you're going to need to have a bit of an understanding of what these things are talking about and why they're important to waves. So superposition and interference is a really important idea. It's what makes a wave a wave. If you superpose or interfere, which means two waves that meet and cancel each other out or add together to make a bigger wave, then that's one of the properties that makes you a wave. The other properties are reflection, refraction, diffraction, and this is the fourth. Now, it's really important that I just highlight that to you now, because when you do quantum physics, this idea is going to come back. This is a wave property. That's really important that you know it, and for now that you just understand what it actually is. And then the final section is just looking at intensity. And again, intensity is just one of these ideas. It follows an inverse square law if you've got a point source. Again, it's something which translates across from a lot of other ideas in physics. For example, gravity follows an inverse square law. And when you start to study infrared, and one of the experiments you may end up doing in the thermal lab, will sort of use this idea of intensity to some degree as well. But you'll also find for the lab work, some of the earlier stuff that you've studied will come up. So, for example, emitting radiation, specific heat capacity, will be things that you'll be using in the lab later on as well. So, quite a big topic, really, waves is, but in all honesty, it's a lot of quite basic stuff you've just got to be aware of. It's not a huge amount to get your head around. It's nothing horribly complicated, but it is quite important and underpinning to a lot of areas in physics.